this section is called Gases in Chemical Reactions, Stoichiometry Revisited. So here it comes around again. So if we have gases as reactants or products, we can't measure that really as molarity. You can't really measure the mass of it, not conveniently, and so we'll typically specify the quantity of gases as their volume at a particular pressure and temperature. And then we'll use the ideal gas law to calculate the moles. So we've got grams to moles to moles to grams. So we can take the volume, pressure, and temperature, calculate the moles. If we're ending up with a gas at the end, we can calculate the volume from the moles. So, an important thing to remember, bless you, at STP, you can use 1 mole is equal to 22.4 liters, the molar volume of a gas. Remember, this is only for gases, okay? You can't use that for liquids. It's really tempting sometimes, but you just can't. Sometimes the pressures given are partial pressures, or you need to calculate a partial pressure from a total pressure, especially like if you're collecting a gas over water. So this is our typical grams to moles to moles to grams plan for stoichiometry. And that's always the place to start. The mole to mole part will always be there. The moles are in the middle and the other things are on the outside. Sometimes you'll have, a problem that's just moles to moles, and then don't make it more complicated by trying to pull grams in there, okay? It doesn't have to include grams. So we start with this, and then if we've got a gas, we might have pressure, volume, and temperature of a gas instead of the grams at the beginning. Or we might have pressure, volume, and temperature of the gas at the end. We could have a gas at the end and a solution with a molarity at the beginning. There's just like so many different combinations, but they're all just variations on this one idea. Grams to moles to moles to grams. If you understand dimensional analysis, that gives you your path. The units tell you where to put the numbers. It's a very doable thing, and this is like one of the central things in Chem 1A. So if you're still a little shaky on stoichiometry, please hit me up and ask me questions, and I will talk to you about it until you say, oh, I get it now, that's easy, right? Or you start crying and decide to go home and change your major, but that's never happened. We're not going to make it a first. Not that I know of. Not that I know of. But the exam coming up next week, there's a lot of stoichiometry on that. And then, it's not going to go away. Stoichiometry is not going to go away. So here's an example. In the following reaction, 4.58 liters of oxygen was formed at P equals 745 millimeters of mercury and T equals 308 K. How many grams of Ag2O decomposed? So, as usual, let's go through and highlight, literally, the numbers. So we've got a volume of oxygen, we have a pressure, and we have a temperature. So we're identifying what we've been given, and then we identify what are we trying to find. Grams of Ag2O. Often there's a question word there, how, what, something like that. So now that I've done that, I'm going to take these numbers and I'm going to write them under the substance that they relate to. So here it's the oxygen gas. Instead of just a mass or a molarity and a volume, I've got 3 things to write here. I've got a volume, a pressure, and a temperature. So 4.58 liters of this, 745 millimeters of mercury, 308 Kelvin. And then the question, how many grams of Ag2O? So under Ag2O, question mark, how many, the unit wanted there is grams. Whoops. So this is a chemical reaction with amounts, therefore it is stoichiometry. So we start with grams to moles to moles to grams and see if we need to switch anything up. So we are looking for grams at the end, so that's fine, we can leave that alone. But are we given grams at the beginning? No, we aren't. We could calculate the number of grams from that information, but then we'd have to convert the grams to moles and we'd be adding extra work. This is our volume, pressure, and temperature, and so we use the ideal gas law to calculate the moles. So here, instead of grams, we've got pressure, volume, and temperature, and the conversion factor here is PV equals nRT. It's not really a conversion factor, but we're going to calculate the moles, and then we'll continue with our dimensional analysis. So first thing is to calculate the moles of oxygen. So N, let's just go over to the edge. N is equal to PV over RT. So we need the pressure. Can we use millimeters of mercury? No, we can't. So we have to convert that to atmospheres. So we're multiplying by atmospheres, dividing by millimeters of mercury. The millimeters of mercury cancel out. And so that ends up being 745 over 760 atmospheres. You can write it as a fraction in your calculation, and that saves you from writing down the number and then typing it in later. If you want to do that, that's of course absolutely fine. So I'm going to call this 745 over 760 atmospheres. The volume, 4.58 liters, that's the unit we need. Then we're going to divide by R, the gas constant. Liter, atmospheres per mole, Kelvin. And the temperature, they gave it to us in Kelvin. That was very thoughtful of them. So then we calculate 745 divided by 760 times 4.58 divided by, open parentheses, 0.08206 times 308, close the parentheses, equals. So my moles, 0.17763 moles of oxygen. And we could guess at 3 sig figs because it seems like all the examples in the book are 3 sig figs. But we can also double check this. Yeah, the volume is 3 sig figs, the pressure is 3, the temperature is 3. So there's my 3 sig figs. To avoid rounding errors, I'm just writing down the next 2 digits. You don't have to write the whole thing. So there's my moles of oxygen. So that's this part right here. Now I finish with dimensional analysis. So I have 2 arrows left. So I'm going to have 2 fractions. I'm doing moles to grams. So moles of oxygen, I don't know how that happened, to moles of Ag2O to grams of Ag2O. This tells us what units go on the tops of the fractions. I take the previous unit and divide. So those cancel out. This one cancels out. With the units in place, it tells me where to put the numbers. Where do I get the numbers for the mole ratio? From the chemical equation, right? This is telling me for every 2 moles of silver oxide, I'm going to get 1 mole of oxygen. So 2 moles of silver oxide to 1 mole of oxygen. And then the relationship between grams and moles is the molar mass, which we have to calculate using the periodic table. So 2 times 107.9 plus 16. Oops. 2 times 107.9 plus 16, 231.8. So 231.8 is the mass in grams of 1 mole. So 0.17763 times 2 times 231.8 equals 82.349 grams. 82.3 grams. When I look at your worksheets, I see people doing the calculations a different way, doing individual steps without units, and a lot of times you're getting the correct answer, but I look at that and it's scary to me. It's like watching someone walk on a tightrope without a net underneath. It would just be so easy to fall off and get seriously hurt, right? Thankfully, there's no bodily injury associated with doing badly in stoichiometry, but it's still scary to me. So if you're one of those people that's not doing dimensional analysis, I strongly encourage you to do dimensional analysis, because it is better. It's just better. What's really interesting to me through the pandemic and the online stuff and having to investigate so much cheating, I've come to realize that people in other countries solve problems in very different ways. And I guess it works for them, but it seems awfully complicated to me, and there seems to be an awful lot of stuff to remember. And so I used to see people write out this whole thing, and I'm like, that's not at all what I taught them to do. And sure enough, on Chegg, there it is. And I guarantee you they did not understand what they are doing. Again, the point here is not to get the correct answer. You're not doing me a favor by getting the correct answer. I already know what the answer is, right? The point here is for you to learn how to do it, right? So that you can do it on an exam. Any questions about this one? Kind of went off on a tangent there. That happens sometimes. So here's another one. And there's a big hint up here in the title, using molar volume. Maybe we should use the molar volume. Wouldn't it be nice if your life came with little chapter headings that gave you a clue? Like, oh, maybe I should avoid the quicksand, something like that. So we don't get those on an exam either. How many liters of oxygen at STP are required to form 10.5 grams of water? So we've got 10.5 grams of water. The other thing is at STP. That's like a free ride ticket or something. At STP means you can use the molar volume of a gas, and that makes things so much easier. There's not really any good place to write it. I'll put it up here. So 1 mole equals 22.4 liters at STP. You can do it without using it, but it's longer. At the very least, though, we need to recognize that this is telling us what the temperature and the pressure are. So I'm going to take my numbers. There's only the one. I'm 10.5 grams of water. And then the question, how many liters of oxygen? So under oxygen, question mark, liters. So We'll start with grams to moles to moles to grams, because that's where you start. We do have grams here. This is the beginning part, so I'm going to start with grams of water to moles of oxygen, but then I'm going to go to liters of oxygen instead of grams. So this is my path. That's my plan for how I'm going to do the calculation. So now we can write the equation. 10.5 grams of water. I have 3 arrows, as I often do in a stoichiometry problem. I just cannot get this 2-fingered moving the screen around thing. That's why those lines appear and then disappear. Grams to moles to moles to grams. So I've got grams of water to moles of water to moles of oxygen to liters of oxygen. It's probably too long. This is the compound that I'm starting with, the one I have the information about. The one with the question mark is the one I'm going to, right? So I'm starting with water, going to oxygen. So I've got grams of water, moles of oxygen, grams of water, moles of water. I should just stop talking. Grams of water, moles of oxygen to liters of oxygen. I think it was better before I tried to explain it. So we'll follow our pattern of putting the units down here to cancel them out. And, dimensional analysis is one of those things that until you do it yourself, you could watch me do it all day long and it still probably won't make any sense. So I've got moles and grams here for water, molar mass. That's another big deal. Need to know how to do that. 2 times the mass of hydrogen plus the mass of oxygen gives us the molar mass of water. So that many grams is 1 mole. Here are my moles in the middle. The mole ratio comes from the balanced chemical equation. 1 oxygen to 2 waters, right? So 1 in front of oxygen, 2 in front of water. And then at the end, liters and moles, that's the molar volume of a gas at STP. And just like the molar mass, it's 1 mole is this thing. See over here, 1 mole is this mass in grams. Here it's going to be 1 mole is the number of liters. So 10.5 divided by 18.016 divided by 2 times 22.4. 6.5275 liters, 6.53 liters of oxygen. Any questions? $6.53 liters.